This meeting is being recorded.
For this video, we're going to review both sections 4.4 and 4.5. And we're going to take a look at specifically here the stability of different isomers. And based on something called heat of combustion, we'll review what that means. We can determine which isomer would be more stable, right? So the relative stability is what we're going to compare here, how they're stable compared to one another. So our potential energy diagram shown down here, it measures the enthalpy or the heat of our bonds, right? If you recall, enthalpy as a measure of bond energy, specifically the heat. We'll call it when a process of combustion occurs, we can form new bonds and release energy. So if you recall, an exothermic reaction would have a negative change in enthalpy, and that's what we see here. So if we were to take these hydrocarbons, so let's start with this one on the left here, and we wanted to perform a combustion reaction. If you recall, we have what, 1, 2, 3, 4, 5, 6, 7, 8 carbons here. We would need 12.5 moles of O2 to fully combust this. And then we see our products listed down here. We, with a combustion reaction of hydrocarbons or carbohydrates, we always have CO2 and H2O as our products. So that's where the 8 CO2 molecules came from. We had 8 carbons in our carbon chain. So what you may notice is that when we go from reactant to product, we have different values listed here. Different amounts of energy are released depending on what isomer undergoes this type of combustion reaction. So what we're actually calculating is the difference in energy between the bonds that were broken and then the amount of energy that's released in the bonds that are formed. So that's what our change in enthalpy value, our heat of combustion, is given down below. So this first starting material, we'll call this compound 1, isomer 1 up here. This has the highest potential energy. So then when it undergoes combustion, we see that the most energy is released to end up at these products down here. So that would mean that this is the least stable, right, this first one, of all of these compounds. The higher the energy, the potential energy, the least stable compound. So over here, we see, or over here rather, this last compound is the most branched isomer of the three, and we see the least amount of heat released, or the least amount of delta H, or change in enthalpy, over here, because it started at a lower energy. And we conclude then that these branched alkanes are going to be lower in energy and more stable than these straight alkanes. So we'll see this trend throughout this chapter when we talk about the most stable compounds. And you can see that there's about 10 kilojoules per mole energy difference between compound 1 and 2, and then even less difference between 2 and 3 over here. So let's move to the second part of this presentation. So section 4.5, we're going to look at some of the uses of alkanes. So you may be familiar with petroleum products and the fact that they are separated through distillation. So based on their physical properties of boiling point, we can separate, right, these different hydrocarbons through fractionation, through distillation. So we get these different fractions as we get higher and higher in boiling point. So the highest boiling point would be for these non-volatile solids. Those are things like waxes, asphalts, tar, and those are the largest carbon chains, so 20 carbons and higher. There's also non-volatile liquids in that carbon 20 and higher category. These are things like greases and lubricating oils. Then as we get smaller and smaller, we see that our boiling point is lower and lower. So things that are only 1 to 4 carbons in length, such as methane, ethane, propane, and butane. Those would be the natural gas like methane, formation of plastics, things of that nature. Utilize those compounds, and then everything in between, right? We have gasoline, we think of octane, but it's really a mix of hydrocarbons 5 to 12 in length and some aromatics as well. And then things like jet fuel, a little bit longer. So that's where all the energy comes from to power your vehicle, right? The combustion of these hydrocarbons and the energy that's released. So how do we create these alkanes? So a process called cracking is used to take some of these larger alkanes. So say we did our distillation of petroleum, we end up with this long, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a dodecane here, a 12 carbon chain. Now we can do this process called cracking, which at very high pressure and high temperature, we can add hydrogen and kind of break this molecule apart here. So somewhere in there, we've cracked this in half, and now we have two smaller unbranched straight chain alkanes. We can also do something called reforming. So if you're into gasoline and anti-knock in your engine, you may be interested in knowing that these linear unbranched alkanes are more prone to knock. So therefore we do this reforming, and that creates branched or aromatic compounds with the right amount of carbons to be used as a fuel source as well. So after these processes are done, we have a higher yield. So that's how we get from petroleum products, from natural oil sources and things into our gasoline using this cracking or reforming process. So that will be in a usable form. So we'll continue with the next section on Newman projections, section 4.6, in our next video.